Welcome to Chapter 1, Module 1, What is Software Architecture? This is your Professor Atif Farid Muhammad. The outline is what is software architecture is and what it is not, architectural structure and views, architectural patterns, what makes a good architecture, and then in the end of the lecture we'll have a summary on this. So what is software architecture? The software architecture is a set of structures needed to reason about the system, which comprises software elements, relations among them, and properties of both. The definition stands in contrast to other definitions that talk about the system's early or major design decisions. Many architectural decisions are made early, but not all are. Many decisions are made early that are not architectural. It is hard to look at decision and tell whether or not it is major. Structures, on the other hand, are fairly easy to identify in software, and they form a powerful tool for system design. Let's look into this with a use case to understand it better. Software architecture is like the blueprint of a building, but for software systems. It defines the structure, components, behaviors, and interactions of a system. Imagine you're building a university management system. The architecture would outline the major components like the student database, course management, grade tracking, and fee payment system. It would also define how these components interact with each other, ensuring the system runs smoothly. In a university system, the architecture might include a user interface layer where students and staff interact with the system through the website or app. Behind this, there would be a business logic layer that handles the core functions like enrolling students in a course or calculating grades. Finally, there is a data layer which stores all of the information about students, courses, and grades. The architecture ensures that changes in one part of the system, like updating the user interface, don't negatively impact other parts like the data storage. For example, when a student enrolls in a course, the user interface layer collects the student's details and course selection. This information is passed to the business logic layer, which checks if the course is available and if the students meet the prerequisites. If everything is okay, the data is then sent to the data layer to be stored. The architecture makes sure that process is efficient and reliable even as the system grows and changes over time. Architecture is a set of software structures as mentioned earlier. The structure is a set of elements held together by relation. Software systems are composed of many structures and no single structure holds claim to be the architecture. There are three important categories of architectural structures: module, component and connector, allocation, and we'll look into this with few examples in a little bit more depth. Module structures. Some structures partition systems into implementation units, which are also known as modules, or which we call modules. Modules are assigned specific computational responsibilities and are the basis of work assignments for programming teams. In large projects, these elements, modules, are subdivided as assignments to subteams. Modules in software architecture are like the different rooms in a building, each serving a specific purpose. In a university management system, modules help organize the system into manageable parts, each handling a distinct function. For instance, you might have a student management module, a course management module, a grade tracking module, and a free payment module. Each module encapsulates the data and functions related to the specific task. The student management module would handle everything related to students, such as their personal information, enrollment status, and academic records. It would have its own database tables, user interfaces, and business logic to manage student data. Similarly, the course management module would deal with course offerings, schedules, and enrollments. The modular structure make the system easier to develop, maintain, and update. If there is a change in how courses are managed, you only need to update the course management module without affecting the rest of the system. Modules also interact with each other through well-defined interfaces. For example, the grade tracking module would need to pull student information from student management module and course information from course management module to assign grades correctly. By keeping these interactions organized and minimal, the system remains efficient and easy to understand. This modular approach ensures that the university management system can scale and adapt to new requirements over time, such as adding new features or integration with other systems. Component and connector structures. Other structures focus on the way the elements interact with each other at runtime to carry out the system functions. We call runtime structures component and connector CNC structures. In our use, a component is always a runtime entity. Suppose the system is to be built as a set of services. The services, the infrastructure they interact with, and the synchronization and interaction relations among them from another kind of structure often used to describe a system. These services are made up of compiled from the program in the various implementation units or modules. Allocation structures describe the mapping from software structures to the system's environment, organizational, developmental, installation, execution. For examples, modules are assigned to teams to develop and assigned to places in file structure for implementation, integration, and testing, as we mentioned in the university management system. Components are deployed onto hardware in order to execute. Which structures are architectural? A structure is architectural if it supports reasoning about the system and the system's properties. The reasoning should be about an attribute of the system that is important to some stakeholder. These include functionality achieved by the system, the availability of the system in the face of faults, the difficulty of making specific changes to the system, the responsiveness of the system to user requests, and many others. Architecture is an abstraction. Now, let me share this with you in the use case that I am discussing in the university management system. And I'll give a pause here so you can read, or you can pause the video to read this slide. All right, let's get to the use case. Architecture in software is an abstraction, meaning it's a simplified representation of the system that focuses on the key components and their interactions rather than the detailed implementation. Think of it like a map of university campus. The map does not show every detail like every tree or bench, but it highlights the important buildings, roads, and paths that help you navigate the campus. In a university management system, the architecture abstracts the complex details of the software into high-level components of their interactions. For example, the architecture might represent the student management component as a single box with inputs and outputs rather than showing every database table, user interface screen, and line of the codes involved. The abstraction makes it easier to understand and discuss the system as a whole. You can talk about how the student management component interacts with the course management component without getting bogged down in the detail of how much component works internally. Abstraction also helps in managing complexity, especially as the system grows. By focusing on the high level view, you can make strategic decisions about the system, such as how to scale it up to handle more students or how to integrate it with other systems. It also makes it easier to communicate about the system with different stakeholders, like developers, administrators, and users, each of whom might have a different level of technical understanding. In essence, architecture as an abstraction provides a clear, manageable overview of the system, making it easier to develop, maintain, and improve. Every system has a software architecture. Every system comprises elements and relations among them to support some types of reasoning. So when the students are enrolled, they need to be in student management, but they need to enroll also within the university system in the courses. So the course management is there for us to assign the courses, and the grade tracking is another component which tracks the grades of the students who has taken some courses. Also, the university bill payment can be another aspect. But the architectures may not be known to anyone. Perhaps all of the people who designed the system are long gone. Perhaps the documentation has vanished or was never produced. Perhaps the course or the source code has been lost or was never delivered. An architecture can exist independently of its description or specification. Documentation is critical. Architecture includes behavior. The behavior of each element is part of the architecture insofar as that behavior can be used to reason about the system. This behavior embodies how elements interact with each other, which is clearly part of the definition of architecture. Architecture includes behaviors, meaning it is not only defining the structure of the system but also how the system acts and responds to different situations. In the university management system, the architecture would specify how the system behaves when a student enrolls in a course, when a professor submits grades, or when a tuition payment is made. This includes workflows, processes, and rules that govern how the system operates. For instance, the architecture would describe the behavior of the system when a student tries to enroll in a course that is already full. It might specify that the system should check the course capacity, notify the student that the course is full, and suggest alternative courses or add the student to a wait list. By including behavior in the architecture, you ensure that the system not only has the right components but also functions correctly and periodically, providing a seamless experience for all the users. Physiological structures, the neurologist, the orthopedist, and the hematologist and the dermatologist are all have different views of the structure of the human body. Ophthalmologists, cardiologists, and podiatrists concentrate on specific subsystems. The kinesiologists and psychiatrists are concerned with different aspects of entire arrangement's behavior. Although these views are pictured differently and have different properties, all are inherently related and interconnected. Together they describe the architecture of human body. So it is with the software. So this is an example of you know different views as different specialists in terms of their speciality. The physician, the surgeon, the specialist look into the structures of human physiological structure in different ways. Structures and views. Let's look into this with a use case. In software architecture, structures and views are fundamental concepts that help in understanding and designing complex systems. Structures refer to the various elements and their relationships within a software system. These can include module structures, which focuses on units of implementation like code modules, the process structures, which deal with runtime components and their interactions. Each structure provides a different perspective on how systems is organized. Views, on the other hand, are representatives or representations of the system from different stakeholder perspectives. They help in visualizing and communicating the architecture effectively. For example, the static view shows the code structure. A dynamic view illustrates the system behavior during execution. The deployment, which view depicts how the system is distributed across hardware. These views are essential for ensuring the system meets the quality attributes like reliability, maintainability, and security, which are crucial for overall success. The module structures, as we discussed earlier, embody decisions as to how the system is to be structured as a set of code or data units that have to be constructed or produced. In many module structures, the elements are modules of some kind, perhaps classes or layers, or merely divisions of functionality, all of which are units of implementation. Modules are assigned areas of functional responsibility. There is less emphasis in these structures on how the software manifests at runtime. Module structures allow us to answer questions such as these: what is the primary functional responsibility assigned to each module? What other software elements is a module allowed to use? What other software does it actually use and depend on? What modules are related to other modules by generalization or specialization? Inheritance come into play here. I will discuss that in detail in terms of the relationships. Component and connector structure. Let's look into this with an example. Component and connector structures are a key concept in software architecture, as discussed earlier, providing a clear view to organize and understand complex systems. In a university management system, this structure helps break down the system into manageable parts, each with a specific role. Components represent the functional units of the system, such as student management module, course catalog, grade tracking system, and fee payment module. Each component encapsulates a set of related functions and data, making the system modular and easier to develop, maintain, and update. Connectors, on the other hand, define the interactions between these components. They specifically tell us how the data and control flow should happen from one component to the other, ensuring that the system works cohesively. For example, when a student enrolls in a course, the student management component needs the enrollment data to the course catalog component via a connector. This connector ensures that the course catalog is updated with the new enrollment information. Similarly, when the grades are submitted, the grade tracking component communicates with the student management component through the connector to update the student's academic record. The component and connector structure promotes a clear separation of concerns, making the system more robust and adaptable. In the university, if the university needs to add new features such as an online learning platform or the LMS, Learning Management System, it can be integrated as a new component with defined connectors to existing system. This modular approach allows for independent development and testing each component, reducing the risk of system-wide failures and making it easier to scale the system as the university grows. Allocation structures. Let's look into this with an example. Allocation structures in software architecture are crucial for mapping software elements to the environment in which they will run. In a university management system, allocation structures help determine how different components of the system are distributed across the available hardware and network resources. This includes decision making or deciding which servers will host specific applications, how databases will be distributed, and how network resources will be allocated to ensure optimal performance and reliability. For example, the student management component might be allocated to the dedicated server to handle a high volume of student data and transactions. The course catalog and grade tracking components could be hosted on separate servers to balance the load and ensure that each component has the necessary resources to function efficiently. Additionally, allocation structures consider non functional requirements such as security, scalability, and fault tolerance. For instance, sensitive student data might be stored on secure server with encrypted connections, while less critical data could be hosted on more accessible servers. Allocation structures also play a vital role in ensuring the system's reliability and maintainability. By carefully allocating resources, the university can ensure that the system can handle peak loads such as during registration periods without performance degradation. Moreover, allocation structures facilitate easier maintenance and updates, as components can be isolated and worked on independently without affecting the entire system. This structured approach helps the university management system remain robust, scalable, and adaptable to changing needs. Structures provide insight. The structures play such an important role in our perspective on software architecture because of the analytical and engineering power they hold. Each structure provides a perspective for reasoning about some of the relevant quality attributes. For example, the module structure, which embodies the modules use what other modules, is strongly tied to the ease with which a system can be extended or contracted. The concurrency structure, which embodies parallelism within the system, is strongly tied to the ease with which the system can be made free of deadlock and performance bottlenecks. The deployment structure is strongly tied to the achievement of performance, availability, and security goals, and the list goes on. Some useful module structures: decomposition structure. The units are modules that are related to each other by is a submodule of relation. It shows how modules are decomposed into smaller modules recursively until the modules are smaller enough to be easily understood. Modules often have products such as interface specifications, code, test plans, etc. associated with them. The decomposition structures determine to a large degree that the system's modifiability by assuring that likely changes are localized. This structure is often used as the basis for the development project's organization, including the structure of the documentation and the project's integration and test plans. The units in this structure tend to have names that are organization specific, such as segment or subsystem. Uses structures. The units here are also modules, perhaps classes. The units are related by the uses relations, a specialized form of dependency. A unit of software uses another if the correctness of the first requires the presence of a correctly functioning version, as opposed to the stub of the second. The uses structure is used to engineer the system that can be extended to add functionality, or from which useful functional subsets can be extracted. The ability to easily create a subset of a system allows for incremental development. Layer structure. The modules in this structure are called layers. A layer is an abstract virtual machine that provides a cohesive set of services through a managed interface. Layers are allowed to use other layers in a strictly managed fashion. In strictly layered system, a layer is only allowed to use a single other layer. This structure imbues a system with portability, the ability to change the underlying computing platform. Let's look into this with an example. Layered architecture is a fundamental design pattern in software engineering that organizes a system into distinct horizontal layers, each responsible for specific tasks. In a university management system, this structure helps manage complexity by separating concerns into well defined layers. Typically, a university system might include layers such as the presentation layer, business logic layer, data access layer, and database layer. The presentation layer handles user interactions, ensuring that student, faculty, and administrators can easily navigate and use the system. The business logic layer contains the core functionalities such as course enrollment, grade processing, and fee calculations. This separation ensures that each layer can be developed, tested, and maintained independently, making the system more modular and easier to understand. The data access layer in a university system acts as an intermediary between the business logic layer and the database layer. It manages data retrieval and storage, ensuring that the business logic can operate efficiently without direct database interactions. The database layer is the lowest level, responsible for storing all the data, including student records, course information, and financial transactions. This layered approach promotes scalability and maintainability. For instance, if the university needs to upgrade the database system, changes can be made at a database layer without affecting the business logic or presentation layer. This isolation of layers also enhances the security, as sensitive data handling can be confined to the database and data access layers with strict controls in place. Layered architecture supports easier troubleshooting and updates. If an issue arises, developers can pinpoint the problematic layers and address it without disrupting the entire system. For example, if there is a bug in the grade processing function, it can be fixed within the business logic layer without affecting the user interface or database. This modularity also allows for incremental improvements. The university can update the user interface to enhance usability and add new features in the business logic layer to support additional services, all while keeping the core data management stable and secure. Some useful module structures is continued class structure or generalization. The module units in this structure are called classes. The relation is inherits from is an instance of. This view supports reasoning about collections of similar behavior or capacity. The classes that other classes inherit from and parameterized differences. The class structure allows one to reason about reuse and the incremental addition of functionality. Let's look into this with an example. Class structure in software architecture refers to the organization of classes, which are blueprints for creating objects within a system. In a university management system, classes would represent the various entities of their behaviors. For example, there might be student class with attributes like student ID, student name, and enrolled courses, along with methods for enrolling in the courses or viewing grades. Similarly, a course class could include attributes such as course code, title, and instructor, and the methods for adding students or updating the course schedule. The structure promotes reusability and modularity, making the system easier to develop and maintain. Each class in a university system encapsulates its data and behaviors, ensuring that changes. Let me recap this so you are clear again. Each class in a university system encapsulates its data and behaviors, ensuring that changes in one class do not inadvertently affect others. For instance, a student class can interact with the course class through well-defined interfaces, permitting students to enroll in courses without needing to know the internal workings of the course class. This encapsulation enhances security and stability, as sensitive data and critical operations as protected within the respective classes. Additionally, class structures supports inheritance and polymorphism, enabling the creation of specialized classes. For example, graduate student class could inherit from the student class, adding attributes and methods specific to graduate students, such as a research topic, and advisor information. This hierarchical structure makes the system flexible and adaptable to new requirements. Data model. The data model describes the static information structure in terms of data entities and their relationships. For example, in a banking system, entities will typically include account, customer, and loan. Accounts have several attributes such as account number, type, savings and checking, and status and current balance. This can also be applied in the same fashion in a university management system. Some useful CNC structures. A relation in all component and connector structure is attachment, showing how the components and the connectors are hooked together. The connectors can be familiar constructs such as invokes. Useful CNC structures include service structure. The units are services that interoperate with each other by service coordination mechanisms such as SOAP. The service structure helps to engineer a system composed of components that may have been developed anonymously and independently of each other. Concurrency structure. The structure helps determine opportunities for parallelism and location where the resource contention may occur. The units are components, the connectors and their communication mechanisms. The components are arranged into logical threads. Deployment structures. Let's look into this in a university system setting. Deployment architecture in software engineering refers to the structure and organization of the physical systems on which the different components of an application are installed. In a university management system, deployment architecture defines how the various software components such as the student information system, course management module, and financial aid module are distributed across different servers and networks. This architecture ensures that each component is hosted on the appropriate hardware and optimize performance, scalability, and reliability. For example, student information system might be deployed on a dedicated server to handle high traffic, while the course management module could be hosted on a separate server to ensure that fast access the course materials for the professors to work with. The deployment architecture also describes the connectivity between these physical systems, ensuring the data can flow smoothly between different components. For instance, the student information system needs to communicate with course management module to update enrollment data and with the financial aid module to process tuition payments. This connectivity is crucial for seamless operation of the university system, ensuring that all components work together efficiently. Additionally, deployment architecture considers factors such as load balancing, failover mechanism, and security protocols to ensure that the system can handle peak loads, recover from failures, and protect sensitive data. The implementation structure. This structure shows how software elements, usually modules, are mapped to the file structures in the system's development, integration, or configuration control environments. This is critical for the management of development activities to build processes. Work assignment structure. This structure assigns responsibility for implementing and integrating the modules to the teams who will carry it out. Having a work assignment structure be part of the architecture makes it clear that the decision about who does the work has architectural as well as management implications. The architect will know the expertise required on each team. This structure will allow us to determine the major communication paths among the teams, regular teleconferences, Wikipedia or wiki updates, email lists, and so forth. Relating structure to each other. Elements of one structure will be related to the elements of other structures, and we need to reason about these relations. A module in a decomposition structure may be manifested as one part of one or several components in one of the component and connector structures. In general, mappings between structures are many to many. So one to one to many to many, and many to one are few relationships in the systems architecture or deployment architecture or software architecture. Modules versus components. A system has client and server. The key is module in decomposition view, whereas client server view has the key in terms of component and request reply. So request response is in the client server view that comes handy for us to look into. This is how a system architecture looks like. Architectural patterns. Let's look into this with an example. Architectural patterns in software engineering provide reusable, consistent solutions to common design problems, promoting best practices and effective communication among developers. These patterns enhancing flexibility, scalability, and maintainability, making software development more efficient and reliable. In a university management system, the layered architecture pattern, also known as N-tier architecture, structures the application into distinct layers, each reasonably responsible for specific tasks. For example, presentation layer handles user interactions and business logic layer manages core functionalities like course enrollments and grade processing, and the data access layer interacts with the database. This approach allows developers to modify one layer without affecting the others, ensuring that the system remains stable and easy to manage. Other notable architectural patterns include microservices architecture, which breaks down the university system into small, independent services that can be developed, deployed, and scaled individually. This pattern is particularly useful for large, complex systems and require high scalability and flexibility. For instance, the student management service, course catalog service, and grade tracking service can all operate independently, communicating with each other through well defined APIs. The event driven architecture is designed to handle asynchronous events, such as real time updates to course schedules or notifications for students. This pattern is highly adaptable for both small and large applications. By using these architectural patterns, university can create robust, maintainable, and scalable management system that meets the evolving needs of students, faculty, and administrators. So shared data repository pattern, as just mentioned, between the courses students and the fee payments can be an example. Client server pattern, as mentioned earlier, the components are the clients and the servers. The connectors are the protocols and the messages that share among each other to carry out the system's work. Common allocation patterns, multi-tier pattern, competence center pattern, and platform. In multi-tier pattern describes how to distribute and allocate the components of the system in distinct subsets of hardware and software connected by some communication medium. This pattern specializes the generic deployment software to hardware allocation structures, whereas competence center pattern and platform pattern have that these patterns specialize the software systems work assignment structure. In competence center, work is allocated to sites depending on the technical and domain expertise located at a site. In platform, one site is tasked with developing reusable core assets of a software product line, and other sites develop applications that use the core assets. What makes a good architecture? There's no such thing as an inherently good or bad architecture. Architectures are either more or less fit for some purpose. Architectures can be evaluated, but only in the context of specific stated goals. There are, however, good rules of thumb. Process rule of thumb: the architecture should be the product of single architect or a small group of architects with an identified technical leader. This approach gives the architecture its conceptual integrity and technical consistency. This recommendation holds for agile and open source projects as well as traditional ones. There should be a strong connection between the architects and the development teams. So I'm not going to read this all. Pause the video and continue with this slide. All right. Structural rules of thumb. Let's look into this with an example. Structural rule of thumb in software architecture provides practical guidelines for designing robust and maintainable systems in a university management system. These rules help ensure that the system is scalable, flexible, and easy to manage. One key rule is to keep components loosely coupled and highly cohesive. This means that each component, such as a student management module or the course catalog, should be independent and have well defined interface for interacting with other components. Loose coupling ensures that the changes in one component do not adversely affect others, making the system more modular and easier to update. High cohesion maintain components means that each component has a clear responsibility, which enhances maintainability and reduces complexity. Another important rule of thumb is to design for scalability from the outset. This involves anticipating future growth and ensuring that the system can handle increased loads without significant redesign. For example, the university system should be able to accommodate growing number of students, courses, and administrative tasks without performance degradation. This can be achieved by using scalable architectural patterns such as microservices or event driven architecture, which allows different parts of the system to scale independently. Additionally, incorporating load balancing and failover mechanisms ensure that the system remains reliable and available, even during peak usage times. By following these structural rules of thumb, the university management system can be designed to be efficient, adaptable, and resilient, meeting the evolving need of the institution. The software architecture of a system is a set of structures needed to reason about the system, which comprises the software elements, relation among them, and properties of both. A structure is a set of elements and the relations among them. A view is a representation of a coherent set of architectural elements. A view is representation on one or more structured. And this is a little bit more in-depth summary. There are three major categories of structures: module structures, component and connector structures, allocation structures. We have discussed all these in quite depth. Happy learning. See you in the next lecture.